Hi, welcome to my channel, JaberTime, where I do math videos from algebra to calculus and differential equations, simplified with examples. If you like this video, hit the like button and subscribe. If you have any comments or questions, leave them down below. And once again, I want to thank you for watching and hope to see you again and again. Thank you. Today we're going to talk about related rates, and the best way to understand this topic is through enough practice of examples. Here we go. I have an example here as a simple example to start. The sides of a square increase in length at a rate of 2 meters per second. At what rate is the area of the square changing when the sides are 5 meters long? To get started, usually the best way is to make a graph, put some letters, some variables, some numbers, and you gotta need some side work before you start actually solving the problem. This is what I mean. Here's a graph. So we do have a square. We do have the same sides. I call them x. The area is a function of x. Instead of calling it y or f of x, it's an area. So as x increases, the area increases. Next, we know that this function is x to the second, x times x. dx dt is 2 meters per second. The side increases with this speed. And they want what rate is the area of the square changing. dA dt equals what? I should write next to it when x is 5, because it's right there. Usually we put a vertical line here and we write next to it x equals 5. But anyway, you got my idea. A picture with some labels, some side work, taking the information of the problem to the side. Now let's get started right here. So we have the area equals x to the second. dA dt. Notice that in regular equations of f of x, we find derivative of f with respect to x. Now, because everything is changing with time, you could go straight forward to dA dt with respect to time equals 2 is going to go down, so it's 2x to the power 1. But since my main variable is not x, it's hidden inside x actually. X varies with respect to time, as you could see right here, 2 meters per second. So I need to use the chain rule, apply it, and move and reach t times dx dt. All right. Now we need dA dt when x equals 5. So we put 5 right here. Notice that I put the units right here because it's a good way to make sure that you're doing everything right and your units should agree. Here we go. 2 is up front, 5 for x, and this dx dt was giving me also 2 meters per second, 2 meters per second. This is over 1, this is over 1. Simplify, so the area changes at 20 meters square per second. Done with this problem, okay? The area of a circle increases at a rate of 2 centimeters square per second. How fast is the radius? Now this is the other way around. The area is given to you as how fast it changes. They want the component r in this case when the radius is 3 centimeters. Let's do it again. A graph, some kind of graph, some kind of side work, then we'll start. Here's a graph of a circle with radius r. We know that the area equals pi r square. A equals pi r square. They want dr dt. How fast is the radius changing when r equals 3? dA dt was given to me, the area changes at 2 centimeters square per second. 2 centimeters square per second. Okay, let's start working now. A equals pi r square. dA dt equals dA dr times dr dt. Notice right here, I did it differently. Why? Because I want to teach. I just don't want to solve problems and move on. I need to make some notes and some ideas while I'm working. Earlier in the previous problem, we straight went forward to the variable t. So we went dA dt. Here, we did not include this idea. But anyway, this right here is true. If you think about canceling dr, I get dA dt, as you could see. What I mean here, in the previous problem, we did not find dA dx. The variable was x, and inside x there was a t. Here, if you want to do it this way, I have a equals pi r squared, dA dr, that's this guy right here, is 2 pi r. 2 goes front. We are finding derivative with respect to r, so it's going to be 2 pi r. You replace that here and you should be fine. If you want to do it the first way, like example number 1, you could do this. dA dt equals pi times 2r to the first times dr dt. Do you follow me? Let me say it again. dA dt equals 2 pi r times dr dt. But that's the same thing right here. So if you use this method or the other way, as long as you're doing the right thing, you should be fine. So that's what we have. 2 pi r dr dt, speaking straightforward to t, or you could use this knowing that dA dr equals 2 pi r. 2 cancels, divide by 2, divide by 2. I get 1 equals pi r times dr dt. Solving for dr dt, divide both sides by pi r, I have 1 over pi r. Now they want dr dt when r equals 3. We're almost there. This is dr dt. When r equals 3, you just plug in 3 for r, and that should do it. All right? One more. A spherical balloon is inflated and its volume increases at a rate of 8 inches cube per minute. What is the rate of change of its radius when the radius is 5 inches? Here's a graph. It's not needed, but just to stay focused. We have the volume of a sphere is 4/3 pi r cube. dV dt, that's right here. The spherical balloon volume increases at this rate, so I write it down. They want the rate of change of the radius, that's dr dt, when r equals 5. Now the problem is more clear in just like math instead of statements. V of r equals 4/3 pi r cube. dV dt, I'm going straight forward to t as my main variable, equals 4/3 pi, 3 goes up front, so this becomes 3r to the second times dr dt, because there is an r is a function of t. Simplify between the 3's. I get 4 pi r to the second without fractions. dV dt divided by this much to leave dr dt, because the focus is dr dt, so I want to leave dr dt by itself. It's kind of hard to write a fraction bar here, so I wrote it with this symbol. Next. So another way to see it, we need dr dt at r equals 5. dV dt was given to me as 8 inches cube per minute. I wrote it as a fraction. It's easier as a fraction to cross cancel. That's how I do it. All right, cancel between inch cube and inch to the second. You will stay with 1 inch right here. Between 8 and 4, you get 1 here and 2 here. So the answer is 2/25 inch per minute. That's how fast the radius changes. Hopefully it's clear, and let's move on. If you want it as a decimal, that's what I have. All right. A hot air balloon is 150 feet above the ground. When a motorcycle traveling in a straight line on a horizontal road passes directly beneath it, going 40 miles per hour or 58.60 feet per second. If the balloon rises vertically at a rate of 10 feet per second, what is the rate of change of the distance between the motorcycle and the balloon 10 seconds later? A quick comment right here. They gave me the units in 2 different ways. You're not going to be able to use this. And if they did not give you this, students might make a mistake and they will use in their calculations the 40. You have in these problems to pay attention to the units. If this is in feet and this is in feet per second, that shouldn't stay mile per hour. That should be converted to feet per second. Here's a picture to get started. As they mentioned, there is a balloon going up and there's a motorcycle that passes underneath it with 40 miles per hour, which is 176/3 feet per second. 1 mile equals 5280 feet and 1 hour equals 3600 seconds. The balloon is rising at a rate of 10 feet per second. This moment happens at a distance between them which is 150 feet. So instead of reading this, I'm just reading the same information on this graph. Let's take another graph that we care about more. Now, after 10 seconds later, after 10 seconds, the motorcycle is going to move and the balloon is going to rise. So we have more distance vertically, and now we have a distance right here. Let's look at this one here. After 10 seconds, the speed or the velocity of the motorcycle is 58.67 feet per second times 10 seconds to give me the total distance. So it's about 587 feet. Now, this balloon is rising at 10 feet per second, and after 10 seconds you multiply that by 10, so it's going to cover 100 feet. So the total distance at that moment is up 150 plus 100, which is 250. So we have 250 here, we have 587. We don't know d yet, but we could use Pythagoras theorem to find d. And we notice that x squared plus y squared equals d squared. As you could see, by doing the graphs with numbers, and I added even more calculations next to it, the work on the side here, I mean the main work, should go a little bit quick. Now, here we go. X squared plus y squared equals d squared. That's Pythagoras theorem. X squared plus y squared equals d squared. Finding derivative with respect to time, x and y and d, they all change with respect to time. So in the 2x dx dt, here 2y dy dt, and here 2d dt dt. Divide everything by 2, or cancel the 2's, I get a cleaner look. Now the focus is what is the rate of change of the distance, this right here. between the motorcycle and the balloon. All right, 10 seconds later. So the main focus is this guy right here. So let's leave this alone, meaning get rid of d, or divide both sides by d, or multiply both sides by 1 over d. It's right here. Now we know this distance, which was done on the side, and this was on the side. I added that to 150 to get 250, but at that moment, after 10 seconds, we don't know d. Here's how you find d. We know x, we know y, x, y, just plug them in, you get d approximate to 638 feet. Back to the problem. We're almost done. This goes here for d. We know x, which is 587. We know how fast the motorcycle is traveling. We know y, which is 250. We know how fast y changes, increasing at 10 feet per second. Right here. Do the math, and I get approximate to 57.86 feet per second. All right. As you could see, my advice for related rate problems is mainly take care of things, underline, take them out to the graph, do any kind of sketch, do enough work, and this will be quick and easy. And one more time, one example is not enough. You need to practice enough. I picked the best examples that are common pretty much in every single calculus book or class. Now, also I'm trying to have pictures here not too big, because I need to keep everything on one page. This way you stay focused with me, and if you wanna, when you get to this level, pause the video. You could just hit the spacebar, as I always mention, hit the spacebar again, it will play. Not only that, every single example will be in the timestamps down in the description. So you could always visit any problem anytime you want. An inverted conical water tank with a height of 12 feet and a radius of 6 feet is drained through a hole in the vertex of the cone at a rate of 2 feet cubed per second. What is the rate of change of the water depth when the water is 3 feet? The best way is do a graph, but we're looking at height and we're looking at radius. So let h be the depth of the water in the tank at time t. Let r be the radius of the cone-shaped water in the time. The radius of the cone-shaped water, of the water. Here's a graph to simplify things. That's what they are talking about, inverted conical water tank. The water is going outflow at 2 feet cubed per second. And the cone is originally 12 by 6. 6 for r and 12 for the height. By similar triangles, now if you take this to a two-dimensional graph and focus on the math part, I get a right triangle up here and another right triangle down here. As you could see, this is the water shaped cone. So we're gonna call this height varies, as mentioned. We're gonna call this r, which varies, as mentioned. Similar triangles, you could build proportions. As long as you stay consistent, you should be fine. You could go 6 to r, 12 over h. You could go h to r, any way you want. Let's just stay focused and do it. I'm gonna go h to r, then I'll go 12 to 6. h to r equals 12 to 6. Cross multiply, divide by 6. You get h equals twice r, which makes sense. If this is twice this, this should be twice this. Now, Notice that I used red for the minus sign because this is where sometimes students make mistakes. If the water is drained, the water volume is decreasing. Because they are describing with words, they did not write minus. You need to put the minus if you know that this volume is decreasing. Feet cubed per second. What is missing, what they want us to do is, what is the rate of change of the water depth? The water depth. That means they want THTT when of the water depth when the water is 3 feet height. It should be 3 feet height. Okay? Now we are ready to solve and start solving the problem. The volume of the water in the tank has a formula. It's a cone shape, which is 1/3 pi r square h. Finding or simplifying this, I have here h equals 2r or r equals h over 2, either way. But since the focus on h, if I leave it this way, I have 3 variables. V is a variable, changes as time changes, r changes, and h changes. That's 3 variables. Our focus on the height, so I need to focus on height and get rid of r. And this is the way to do it. So r is h over 2. H over 2 for r. Now, in this case, I don't have 3 variables. I have only 2, which is h and v. Clean it up. Now it's clean. Now let's jump to the differentiation and find the derivative with respect to time. And this time I have v and h. dv dt, that's the left side. Pi over 12, pi over 12. 3 goes up front. 3h to the second times dh dt. Now if you pay attention to these numbers, I have 3 and 12 simplifies to 4 down. And now I have dv dt, which we agreed on. That goes right there. And the height is 3. And this is our focus. So we have, as I mentioned earlier, I don't want to read the whole thing. Do the math and solve for this. Be careful with the units. My answer is negative 8 over 9 pi feet per second. Why negative? It should be negative because the height of the water decreases as the volume decreases. So the depth of the water is decreasing at a rate of 8 over 9 pi. 8 over 9 pi. So if you write decreasing, you don't write the minus sign. Feet per second. You see, it takes a lot of work and takes practice. A graph, labels, do some work on the side. The idea right here is to merge these 2 letters and make it only one. And then this v equals pi over 12 h to the third is ready to be used. Then you go back to your numbers and plug them in. A 13-foot ladder is leaning against a vertical wall when John begins pulling the foot of the ladder away from the wall at a rate of 0.5 feet per second. How fast is the top of the ladder sliding down the wall when the foot of the ladder is 5 feet from the wall? Too many numbers and too many things, but let's make or look at a figure or graphs to understand more. Here's the wall. Here's the ladder. It's 13 fixed. As John pulls the bottom of the ladder away from the wall, the top of the ladder is gonna go down. So if you think about two-dimension figure, I have X and H, and this is not D, this is fixed, 13 in this case. As you can see, every problem has its own way of handling right triangles or others. You have to be careful. But notice that X increases, and instead of calling it Y, we call it H for the height, decreases. Keep that in mind. The x dt was given to me up here 0.5 feet per second, or half feet per second. When x equals 5, the right triangle says 5 square plus h square equals 13 square. So when this is 5, I could find the height. At that moment, it's 12, just using Pythagoras theorem. So when this is 5, this is 12, and this is always 13. This is more detailed writing of describing what we have here. Let h be the height. Let x be the horizontal distance. We have x squared plus h squared equals 13 squared. That's 169. Finding derivative now, this is the main part. Everything here is to get ready to this part. With respect to time, 2x dx dt, 2h dh dt, and that's of course 0. Divide everywhere by 2. I get a cleaner look, and our focus is dx dt. Let's go back to the problem. How fast is the top of the ladder sliding down? So no, dh dt. This is our focus. So we need to keep this by itself, not this. We have dx dt, but we need dh dt. When x is 5, we found that h is 12 from here, and dx dt is increasing at 0.5 feet per second. Do the math, feet cancels, 1 stays, and second stays. The answer is dh dt is negative. See, I try to make sure that the negatives are clear, not very tiny symbol, negative sign. 5/24 feet per second. That means the top of the ladder slides down the wall at 5/24 feet per second, and that should do it. This is related race, as I mentioned. Few examples is not enough for every single student. You need to practice more and more. If you first time see a ladder problem and you see it on an exam, you're gonna wonder and panic and start saying, how do I start? Am I doing it right or not? I would say, as much as you can, practice and see enough problems for related rates. They come in a lot of different ways. I try to pick my best, the best problems that repeats a lot, and in the coming future, if it's needed, I'll add more, not to the same video of course, but I'll call it related rates number 2 or part 2. Okay, I am recording another video after this, so thank you for watching. Thank you. Thank you for watching. If you like this video, hit the like button and subscribe, and I'll see you next time. Thank you.